Hello everyone and welcome back to the C++ 3D game tutorial series. Today we will see how to make a post-processing effect from scratch. First of all, what is a post-processing effect? A post-processing effect is a graphical effect that is applied over an image or texture once the scene of a movie, or in our case of a 3D game, has been processed or rendered on it. It is commonly used to add enhancements to the final scene, like ambient occlusion, crepuscular rays, also called God rays, anti-aliasing, depth of field, Gaussian blur, to name a few. Today we will make a post-processing effect called Distortion effect, through which we will create the hyperdrive effect when we move the spaceship in turbo mode. Let's see how a post-processing effect can be achieved. First, we create the render target in which we render the final scene of our 3D game. Today we will use our 3D space shooter demo. Second, when we render the scene on a render target, it is not rendered immediately on the screen, and that's why this kind of rendering is also called off-screen rendering. In order to render the final scene on the screen, we have to draw the rendered target by means of a mesh, in particular a quadrilateral mesh. Third, we apply a vertex and a pixel shader when we draw the quad mesh in order to apply the final graphical effect. Very well, now we can start the implementation. As first thing, let's add a new feature and let's call it post-processing demo. Let's create a new class with the same name. Now, since we want to apply the post-processing effect to the space shooter scene, let's copy and paste the space shooter demo class files into the post-processing demo class files. Let's rename Space Shooter Demo with Post-Processing Demo in both the H and C++ files. This can be done by pressing Ctrl F. We can finally use this class in the main C++ file. Let's see if everything works fine. Well, at this point, let's add the render target and depth stencil textures as attributes of the post-processing demo class. As we have already done in the previous tutorial, in particular in the mini-game class, let's create the two special textures. Since the render target and subsequently the depth stencil will have to cover the entire window area, let's set their size with the window size. Now that our textures are ready, let's use them in the render method. Here we have to simply bind our render target into the graphics pipeline in order to render our space shooter scene on it. Let's do the same thing we've already done in the last tutorial. And at this point, let's move the part in which we bind the swap chain after the part in which we render the scene. So far so good, now we are rendering our demo off screen. That means if we launch now our demo, we will see nothing on the screen. As we have seen in the introduction, we have to create a mesh with the shape of a screen. So a quadrilateral mesh composed by two triangles, like this one, in order to draw the render target on the screen. We've already seen how to make this kind of mesh a lot of time ago. Now we will remake it in a more correct way by extending our Mesh Manager and Mesh classes. Let's do it. Let's go to Mesh Manager class and let's add a new method called createMesh. Here, let's add all the necessary parameters in order to fill the various parts of a mesh, that are the vertex list in order to create the vertex buffer, the index list in order to create the index buffer, and the material slot list, useful to subdivide the various parts of a mesh with particular materials. Let's implement the method that is similar to the createMesh from file method. At this point, we have to pass all these parameters in the mesh constructor. So let's create the new constructor method in the mesh class, and let's add the same parameters. Here we are lucky because the necessary code to create a custom mesh is already done. We have only to copy and paste it and replace the old parameters with the new ones. The only new thing to do is to fill the material slot list of the mesh with the one provided through the parameters. Now we can turn back to the Mesh Manager class and finalize the Create Mesh method implementation. Very well, now we can create any custom mesh we want. So let's go to post-processing demo H file and let's add a new mesh member called quadMesh. Let's create it in the onCreate method. Here we have to call the createMesh method of MeshManager class by passing all the quadrilateral mesh values. Before to start, let's see what values we have to use in order to create a quad mesh. As we have already seen in the previous tutorials, in particular in the earlier videos about the rendering of a triangle and quadrilateral, in order to render the various meshes on the screen, the various vertices must be transformed from world space to screen space in the vertex shader. The screen space is a b-dimensional coordinate space that represents the screen. The x-axis that represents the width of the screen goes from -1, that is the left side, to 1, that is the right side. The y-axis instead, that represents the height of the screen, goes from -1, the top side, to 1, that is the bottom side. All the vertices of the various primitives that resides inside this area will be rendered. The other ones will be simply discarded. That said, the purpose of our code mesh is to draw our rendered target in the entire screen area. That can be the window area in the window width mode or the screen area in the full screen mode. To do so, we have to use the just mentioned boundaries of screen space as vertices of the quad mesh. So let's create the vertex mesh list. Then let's create the index list. And as last thing, let's create the material slot list. Here we have to define only one material that covers the entire quad mesh. So let's set a start index of 0 and let's set a number of indices of 6. Cool, our quad mesh is ready. Now let's start to make the material. Let's call it post-process material. And at this point we should use two new shaders for the post-processing effect. So let's add a new filter in the global shaders and let's call it post-process effect. Let's add the vertex shader and let's call it post-process VS. And let's add the pixel shader and let's call it distortion effect. Now let's copy and paste the skybox vertex shader. At this point we can delete a lot of useless code. The only thing we have to do here is simply to output the position and texture coordinates of the quad mesh to the rasterizer without touch them, because they are already transferred in screen space. Let's copy and paste the skybox pixel shader. Here, let's leave only the position and texture coordinates attributes. That's enough for now. Let's come back to post-processing demo and let's pass this shader to the post-process material. Now let's add the render target texture into the material. Good, we have nearly finished. An important thing to do now is to resize the render target during the window resizing. So let's go to the onSize method and here let's recreate the render target and depth stencil with the new size. Obviously, we have also to remove the old render target and replace it with the new one. Good. As last thing, let's go to the render method and let's finally draw our quad mesh with render target over it. Here we have to fix some issues in the setMaterial method of graphics engine class. Here we have to set the constant buffer only when the constant buffer is available, and so when the pointer is not null. And we have to set the texture only when there are textures available. That's all, folks. Let's see if it works. And it works. It seems that nothing has changed, but currently we are rendering the scene over a quad mesh that covers the entire screen space. And not only that, since now we are rendering our screen through pixel shader, we can apply any sort of effect over it. Let's start by applying a simple effect in which we multiply the color of the scene by 4. And here it is. Let's multiply now the color with a little number like 0.5. Obviously now the scene is dark. Very well, this kind of effects are called post-processing effects. Post-processing because they are applied after the processing or rendering of the scene. Let's move on and let's make a more advanced effect. Let's make an effect where we draw a red circle in the middle of the screen and that covers the entire screen area. In order to do that, we have to transform our texture coordinates from the range 0, 1 to -1, 1. In this way, we place the circle origin in the middle of the screen. At this point, in order to draw a red circle, we have to multiply the color of the scene with a red color, but only when we are inside the circle area. But how can we determine when we are inside or outside of the circle area? Here we have to apply some linear algebra formulas, where we calculate the length of the just transformed texture coordinates. If the length is less than 1, that means we are inside the circle, otherwise we are outside. Very well. Let's see if it works. And it works. So far, so good. Let's move on with the next effect. Let's exploit what we have done so far. Now we want to apply a distortion effect inside the circle area. To do so, we have to make a function called distort. Let's add a float2 parameter that represents the texture coordinates transformed into the range -1, 1. What we have to do now? We have to pass the texture coordinates into a particular function called a10(2). a10(2) is the two-argument arctangent. It is used to convert the Cartesian coordinates defined by x and y axis into polar coordinates, defined instead by a radius and an angle. In particular, a10(2), by passing the y and x values, retrieves the angle created by the vector xy. The radius, as we have already seen previously, can be retrieved by calculating the length of the vector xy. At this point, how can we obtain the distortion effect? Well, we should modify the radius in order to move the provided texture coordinates from the original place to another one. The radius can be modified with any kind of math function. For now, let's use the power function, with radius as base and the value 2 as exponent. This will create the distortion effect. Once we have modified the radius, we have to transform again the polar coordinates to the Cartesian coordinates. In particular, the x value is obtained by multiplying the new radius with the cosine of theta. The y values instead is obtained by multiplying the new radius with the sine of theta. Here we go! We have now the Cartesian coordinates in the range -1, 1. To simplify a bit the work, let's reconvert the values range from -1, 1 to 0, 1. And that's all. Now, when we are inside the circle area, we call the distort function and place the result in a UV variable. When we are outside, instead, we simply use the original texture coordinates. Good, let's see what happens. That we obtain a distortion. This kind of distortion seems like a big bump. It doesn't seem to be so suitable for our space shooter demo. Let's exploit this effect to create the hyperdrive effect. We have only to reduce the exponent used in the power function with a value between 0 and 1. Let's set 0.5. And here we go. We can enable this effect when we move our spaceship in turbo mode. In order to do that, we have to modify the exponent of the power function from code. We can do this by making a new constant structure in which we can add an attribute called distortion level. Then, in the post-processing demo C++ file, let's create the corresponding C++ structure. Let's call it distortion effect data. Now, in order to modify the distortion level during the gameplay, let's add a new attribute in the post-processing demo class. And let's call it again distortion level. Let's set an initial value of 2 for now, and let's pass it to the distortion effect data object. In the end, let's pass the effect data variable as parameter to the setData method. Let's see if it works. And it works. Let's set the initial value of distortion level to 1. In the end, we have to modify the distortion level during the update of spaceship movement. So let's go to update spaceship method, and here when the turbo mode is enabled, and we are moving the spaceship, so when the forward variable is not equal to 0, let's decrease of 0.5 unit each second the distortion level. When the distortion level reaches a value lower than 0.6 units, let's block it at that value. Now let's handle the case in which the turbo mode is disabled. Let's redo the same thing by increasing the distortion level always of the same amount. Then, when the distortion level value is greater than 1, let's block it at 1. Let's see if it works. And it works. Let's make some improvements by reducing the camera distance in the update third-person camera method from 25 units to, for example, 19 units. Good. There is a problem though. The input system seems to have some delay problems when we press and release the shift key in some cases. So let's go to the input system C++ file Here the problem seems to be related to the getKeyboardState function. Let's use a more reliable function to retrieve the various key states. Let's use the getAsynchronousKeyState function. Let's update the type of keystates and old keystates vectors from unsigned int to short. In the end, let's change again the type in the memory copy function. Let's see if now it works. And it works. That's all for now, folks. Today we have seen how to make a post-processing effect from scratch. I hope you enjoyed this video. See you soon. Thanks for watching.